making a lithium enolate, the lithium ion will effectively block access to the oxygen atom, and then you see a decreased amount of oxygen alkylation. So we did the same thing. We made lithium enolates, tetramethylammonium enolates, and the classic DBU enolates. We put them into the same reactions with the same solvent, and what we saw is that we actually, as long as you use the same solvent, you get pretty much the same ratio. So when you react with ethyl iodide, you get about 70-30 split. And when you react this with benzyl bromide with these different counterions, you get 70-30 split the opposite way. So it didn't end up mattering too much with our cyclic enolates. So we had to choose which counterion to settle on then. So we ended up settling on that tetramethylammonium enolate because it has a minimal impact on the 1H NMR spectrum. You know, it's just going to be one big singlet. And it produces salts that are more soluble than, say, a lithium salt or a potassium salt, something like that. So the salts are soluble. So the tetramethylammonium enolates then could be used to do a study of benzyl bromides, and even more so, we could do substituted benzyl bromides. So if we vary the electronic characteristics of the benzyl bromides by putting different substituents in the para position of the ring, we can maybe do a kind of a Hammett type study where we're looking at these ratios while tuning the electronics of the electrophile. So we tried to observe a pattern by doing these reactions in THF, and what we saw was that we could see a kind of a pattern forming, which is that you can see going down the list that when the substituent gets more electron withdrawing, you see an increased amount of O-alkylation. So you can see that on both sides. So stopping with the results for a second. So everybody knows the reactions I'm showing you do one thing, but if you ask somebody to do a reaction with an enolate and methyl iodide in the lab, you would get C-alkylated products. So why is that the case? Why are these reactions I'm showing you doing something different? So to help answer that question, we contacted Dr. Martin Broyst in the University of Cologne, and we asked him to run some Marcus theory-based chemical computations on these reactions to help us find an answer. So his calculations managed to give us an interesting look into why these things kind of might be happening. So we found out that if we go back to the Marcus equation, that O-alkylation has a lower intrinsic barrier than C-alkylation in all cases. So we actually expected this to be the case because of something called the Hotz rule, which states that intrinsic barriers will go down, they'll decrease as you go further to the right in the periodic table. So we see that's a C-alkylated product. So these products here are more thermodynamically preferable in all cases studied than their O-alkylated counterparts. So this number here is the energy difference between them, the Gibbs energy difference between them. But for acyclic enolates, the C-alkylated products are much more thermodynamically preferable. So this one is much more preferable than its O-alkylated alternative. So you can see that this value I've highlighted here in red is much more negative than the counterparts in the cyclic enolates. So these concepts and kind of how you can use them to predict the outcomes of the reactions, it'll be a bit more clear in the second half of the talk. I could talk about these computational results all day, but obviously in the interest of time, I'm just going to use a better example near the end of the talk to show how you can use these numbers in coordination with the intrinsic barrier numbers that we calculate to maybe predict the outcome of one of these reactions. So just to give a quick conclusion on this section, we looked at a few different aspects of reactions of cyclic enolates that produce results that contradict the hard-soft acid-base theory. So one kind of headline result for sure is when you use THF and ethyl iodide in a reaction with all these cyclic enolates we studied, you get over 90% O-alkylation in THF. Again, you wouldn't really expect that with the soft ethyl iodide reagent. So we've seen that when you use deuterated methyl iodide or methyl iodide, a solvent effect can have a massive influence on the O versus C ratio that you see. Again, not really something you can predict. And we also had a look at the counterions effects, and we found that in our examples anyway, with the cyclic enolates, it didn't turn out to be that big of a factor. So we hope that we can use these numbers that we got from our calculations to maybe build a speculative model that will help us figure out what's going on in the reactions. So the second half then is just the ambident nucleophilicity of diazine N oxides. So again, diazine oxides like this pyrazine N oxide that I've drawn down here, they can react at either their nitrogen or oxygen atom. And when you try to apply hard-soft acid-base theory principles to these, you run into an issue straight away, which is which side is hard and which side is soft. So it's not really that obvious as it was in the case of the enolates. So another problem you run into straight away when you're trying to do an ambident reaction of these types of compounds is identifying the products that you actually form. So if you imagine the spectra of these two compounds that I've drawn here, they would be fairly similar either in proton or carbon. So to decisively determine the outcome of these reactions, we needed to use a technique that would tell us definitively what's forming. So we made the decision to use this really clever technique of 1H15N HMBC spectroscopy. So to understand how this would work in reactions of ambient nucleophiles, first we had to do some reactions where there could only be one product. So for example, with this pyrimidine here, if you methylate it, it has to methylate on nitrogen. So then we ran the N-methylated pyrimidine in a 1H15N HMBC spectroscopy, and you can see that there's a correlation that forms between the methyl group and the nitrogen that it's attached to. So you can see that this methyl group is connected to this nitrogen, and we can tell exactly what ppm value is, and there's no correlation to the other nitrogen. So it's a pretty neat way of telling. So we alkylated a few of these heterocycles that can only alkylate in one position, and we found a trend for the ones that can only alkylate on nitrogen and a trend for the ones that can only oxidate or alkylate on the oxygen of an N oxide. So these trends are summarized just down here below. So when you N-alkylate a nitrogen heterocycle, the nitrogen chemical shift of that nitrogen will go down by about 100 ppm. The methyl group of the carbon shift of the methyl group will have a certain distinctive shift, and then there's also an observable ring correlation. And then for O-alkylation, there's a corresponding set of results that you get. So importantly, the nitrogen shift goes down by about 40 ppm. So this could be really useful to some people working with heterocycles in here to tell if you've alkylated on an oxygen or a nitrogen of your compounds. So we are lucky to publish that to maybe be helpful to someone else as well. So now we can definitively assign the products of these reactions of hard and soft electrophiles. So as before, we set up the reactions in a way where we could directly examine the reaction mixture, and we used deuterated acetonitrile as the reaction solvent. So what we saw is that the preferred site of addition between similar ambient nucleophiles, like the ones shown here, can actually change even when you use the same electrophile. So you see here that with a reaction with methyl triflate, the quinoxylene oxide and the pyrazine oxide both favor the N-methylated product in about a 90-10 split. But then when you use the pyrimidine oxide, it actually favors the O-alkylated product. So this is just such a really nice result. It just perfectly encapsulates what we're trying to say. Between these two very similar ambient nucleophiles, you get a complete inversion of the regioselectivity, and it's just not something you can really expect. So at the risk of repeating myself, you can't really predict this using hard soft acid base theory. So we had to again turn to our collaborator, Dr. Martin Breutz, to maybe run some calculations on these reactions using methyl triflate to see maybe did the calculations give us an idea of what's going on. What we find is the calculations do give us a way of potentially explaining why this happens. So in order to calculate the activation energy, Martin needed to calculate two quantities, so this intrinsic barrier and the Gibbs energy of reaction. So in all cases that he ran these calculations on, we found that the intrinsic barrier for oxygen alkylation was lower. And that's, again, something that we expect because of the Hotz rule. So that means if the two products are thermodynamically not very different, then you would expect to see O-alkylation because of this lower intrinsic barrier. But what the calculation suggests is that for pyrazine N oxide, the Gibbs energy of reaction is much lower for the N-alkylated product than it is for the O-alkylated product. And when you plug these numbers into the Marcus equation twice, and then you get two activation energies, you'll find that the thermodynamic preference, the very large thermodynamic preference for the N-alkylated product, results in a lower activation energy for the N-alkylation process. So then it becomes kinetically preferred, and that is the product you see. And when you do the same thing for the pyrimidine N oxide, you'll see that yes, it's intrinsically preferred, and also the difference, the energy difference between these two products is not very big. That means that the intrinsic barrier is the dominant factor in the Marcus equation, and you end up seeing predominant O-alkylation. So the really nice part about these results is that...
Sorry, Kevin, just to interrupt. We're at 15 minutes now.
Okay, perfect. Yeah, I'm just nearly there now. So
yeah, that's fine. Thank you.
So this method of calculation not only predicts the inversion of regioselectivity you see between these two nucleophiles, but it actually approximates the ratio that you see as well. So when you plug the differences in their activations into energies into this modified kind of I-ring equation here, we get these numbers here where the calculated ratio that we'd expect to see, and it's roughly what we see in the lab. So I think this nice agreement between the computational results and what we see in the lab is what makes this study quite nice. Oh, just to finish up with some graphs. So if we represent what I was just talking about there graphically, it looks a bit like this. So here you have the reactant parabola in the middle, and the product parabolas of the N and O alkylation processes sit on either side. So the points where they intersect are the activation energies for each process. And so you can see it here for the pyrimidine and oxide, the intersection point for the O alkylation process is lower. So this is the kinetic product that we see. So even though the N alkylated product is more thermodynamically preferable, there is a small difference here, but the difference is not very big. That means that the intrinsic preference for O alkylation predominates, and O alkylation is what you see. And when we look at the other case with the pyrazine and oxide, there's a huge thermodynamic difference between the two products. And this huge thermodynamic difference allows the Gibbs energy reaction to become the dominant factor in the Marx equation. And the intrinsic preference for O alkylation is overcome. And now the barrier for N alkylation is lower than that for O alkylation. So if I just superimpose them on top of each other, it might just be a clear picture of the same thing. Basically, just this large thermodynamic difference between the two products is what causes that initial intrinsic preference for O alkylation to be overcome, and it kind of explains why you see the difference in regioselectivity between the two nucleophiles. So I'd just like to acknowledge everybody in the game building in UCC who I work with and the people who helped make this happen, and thank you all for your attention, and I'd be happy to take any questions if you have them.
That's excellent. Thank you very much, Kevin. Really nice presentation. You've done a lot of work there. And we have time for some brief questions, if anyone would like to add them to the comments box. You mentioned heterocycle reactions as being particularly applicable to this work. Have you identified any commercially or industrially important reactions that can immediately benefit from this?
I wouldn't say commercial or industrially, but we've looked, say, in the literature, and we found some examples where people were doing reactions with hard electrophiles, and they expected certain products to form, which were kind of essential for their next step. And they assumed that they alkylated on the oxygen, but in reality, they very likely alkylated on the nitrogen, and their next reaction didn't work, and they didn't know why it didn't work. So we included that in our publication about it. So it does go to show you that these things do happen, but not in.
Yeah, no, excellent. No, very good. And we've one quick question here from Owen McGargle. So did the calculations explain the solvent differences you observed too? And if so, what has changed?
So the calculations don't take the solvent into account in a kind of as meaningful a way as they could. I think we just apply this. The solvent is applied as a kind of continuous medium of whatever the dielectric constant, I think, of the solvent is. So I don't think the calculations are able to explain the inversion that you get that way. But I think that may be a limitation of the calculations rather than that we didn't ask about it, if you know what I mean.
Perfect. Brilliant. No, thank you very much, Kevin. Excellent talk. Just in the interest of time, we'll move along. So our next speaker is Christopher Murnaghan. So Christopher, if you would like to share your screen, please do. So you're very welcome, Christopher. So the title of Christopher's talk is The Synthesis of Advanced Biomass Models and Model Compounds. So Christopher, the floor is yours.
Thank you. So hi everyone. So the title of my project is Synthesis of Advanced Biomass Model Compounds. So a bit of background to begin with. So if we look at biomass is formed from three major components. So you have lignin, which is the sole aromatic component of biomass. It's formed from the radical coupling of three monolignol species. You have hemicellulose, so it's all carbohydrate based. So you have xylose, galactose, mannose, glucose, all in there in a sort of irregular pattern. And then in the more regularly arranged fashion, you have cellulose. So cellulose is glucose molecules bonded in a beta 1,4 fashion. So if you look at these three species, you can see that they have the potential to have compounds of interest if they're broken down in the correct manner. So we just need to find the correct manner of doing so. Now, whenever you try and go and break down lignin coming from biomass, the more you try to break it down, the more it fights back. It's kind of like a Rubik's Cube sort of fighting back. So the best way that was used or have been found in the literature to sort of fashion catalytic systems and hone them were to synthesize models which have the linkages, same linkages found in lignin. So there was some very representative models have been synthesized within the literature. So see, these are some of the models which we use in our group. So guaiacol in the left-hand side here, just straight out of a bottle, it has the simplest functionalities found in lignin. It's aromatic, it has a free phenol, and has a methoxy group. So, you know, on a basic level, you know, it can be described as a subunit of lignin. You sort of increase complexity, you move here to the beta-O4 model dimer. You see here that along this skeleton here, so that's the beta-O4 sort of frame. That is the most common linkage found within lignin. It's also the most published about in terms of catalytic degradation, primarily because it's easy to synthesize, and also it gives you a bit of a morale boost, a bit of an ego boost, because it always gives you really good results, because this benzoic alcohol can be easily oxidized, and that in turn makes the full structure of the compound quite labile and will just break apart under most conditions. If we increase a bit more complexity, we go to this beta-5 model here. So you have this benzofuran functionality, and then this aryl linkage here. Now this is probably the second most common linkage found within lignin, and it is not widely reported within the literature to be broken down using any catalytic techniques. I'm going to talk in a few minutes about the paper we recently had published breaking this model of this down. But yeah, not widely used. And then one that's not used at all within the literature is one that was synthesized within our group. So this hexameric model here, it has 6 aromatic rings, and per mole of substrate you have 2 of the beta-5 linkages and 2 of the beta-O4 linkages. And at the center you have this biphenyl linkage here, extremely strong bond. And the catalytic systems we've used before have been no good in trying to break this bond down to produce the species in which it is composed of. So if we move on to lignin carbohydrate complexes, so as you can imagine, these are formed from lignin and carbohydrates. So whenever you break down biomass, you separate it into lignin and carbohydrates. However, there's a portion of that there becomes mixed within the system, and they actually form covalent bonds to each other. So it's kind of like this, a mixture of these. So they have the mixed functionalities of the two, of the lignin and the carbohydrates. So if you see along the bottom here, these are 6 bonding patterns that are seen within nature between lignin and carbohydrates. You see that the orange box, the phenylglycosidic, is the one that we'll be focusing on today, because that's the synthesis of the compounds that we have focused upon. A bit of a timeline here about lignin carbohydrate complexes. So they date back to 1935 when they were first proposed. So this lignin-xylan structure was proposed by Hibbert whenever he's breaking down wood pulp. He's saying that this was one of the most prevalent pieces found within the composition of the wood pulp. Now, it wasn't again until 54 when it was revisited by Merriweather, when the structures were actually proposed, and then to 54 again, where Bjorkman, through fractionation, actually isolated some of these complexes. Now, that's it. There was a massive lull until 1998 in the literature, where Toika in 98 and 99 synthesized some of these model compounds. So they're shown here on the left-hand side. So you have the beta-O4 framework, and then you have here xylose, and then that's bonded to another, so here it's galactose, and another xylose here. So the both ones here. So in terms of our prior work and motivations, we mentioned earlier on the beta-5 model dimer, that's this one here. Now we used titanium dioxide mediated photocatalysis and UV light to break down this compound, as it has never been done before in the literature, and that's basically where we're at. So we work between synthesis and photocatalysis. So we see here that the degradation of this compound produced these 4 products on the right hand side. So you see the consumption of this alkene to produce a diol, and then the elimination of the guaiacol side chain, and so on, another elimination, and then the formation of another diol here. So these 4 were separated and elucidated. And you can see here that underneath the arrow is the thing that we don't want to be using. We don't want to be using organic solvents. So we had to use acetonitrile, principally because this model dimer was completely insoluble in 100% water. So we had to use that co-solvent in order to get any activity out of the system. So lignin carbohydrate complexes, why do we want them? We want to make basically these models of biomass water soluble, and we want to use the water soluble functionalities to be able to test these catalytic systems, such as the titanium dioxide mediated photocatalysis. So we want to use that there because that is a very up and coming field in terms of biomass valorization and lignin valorization in particular. So we began and we thought that how can we best link these sugars to the model compound. So we thought that phenylglycosidic would be the most attainable linkage because it's the most easiest to introduce. We thought that the use of a trichloroacetamidate was good because ease of introduction and a very stable compound. By way of comparison, we tried the bromide, and the bromide was quite resistant to be to work with, and I don't know, we're not sure why, but we found that this trichloroacetamidate was much better in terms of chromatographic separation and stuff like that there. So if you look here on the left hand side, the trichloroacetamidate has been used previously in massive total syntheses, and you can see that, thank goodness, our compounds are much less complicated than these here. So we thought that if it can be applied to these, it can be applied to our more simpler work. So we began the synthesis with glucose. We complete acetylation of glucose using acetic anhydride and sodium acetate, produce pentaacetate. The selective removal of the anomeric acetate by a modified version of Ellervick's benzylamine transformation. So they used polymer-bound benzylamine. We used just neat benzylamine because we found that if you use polymer-bound, it actually costs so much if you want to do this in a preparative scale. So we want to do this in sort of 10, 20 gram scale, so we had enough of the activated glycoside in order to produce enough of the model compounds. So we used the neat benzylamine, no appreciable loss in yield. So this is roughly the same sort of yield as they got in the publication using the polymer bound. Whenever we had the free hydroxyl lane, we just installed the trichloroacetamidate unit by reaction of trichloroacetylnitrile with DBU, and you got the 70% of the activated glycoside and the 1 to 0.06 alpha to beta ratio. So if we talk first of all about why you're getting the alpha to beta ratio, you see here you're getting sort of this this leaving group is going to go, and you're going to get the feeding of the electrons in here and producing this planar intermediate here. So it has been previously described as a pure SN1 reaction where you can actually get attack from both sides. That explains why you get the alpha and the beta anomers. We always see the majority of the alpha anomers in all of our products. So these are the products arising from the glucose-based trichloroacetamidate. So we've seen here, if you build the complexity, you in some cases decrease the yield, but as always, the alpha has always been the predominant anomer here. So we see the phenol to guaiacol, and then we increase complexity. So this is the beta-5 molecule we discussed earlier on. So now this is completely soluble in water. So we have eliminated the need for the organic co-solvent, which is a plus. So we thought, let's make our lives more difficult. Let's increase the complexity of the sugar system. So we added another glucose molecule and we used cellobiose. So cellobiose is 2 glucose molecules bonded in 1,4 fashion, so kind of like a dimer of the cellulose. And we used the same route to produce the activated glycoside, so the same acetic anhydride and sodium acetate, and then the benzylamine and the trichloroacetylnitrile to provide this here in 74% yield. And then we used the Lewis acid boron trifluoride diethyl etherate with the phenolic species pictured here. So guaiacol, acetylvanillone, isoeugenol, this ester here, and this here ethyl ester here. So we see moderate yields in all of them. And again, the alpha was the prominent in most cases. So that was cellulose sort of covered. We then sort of focused towards hemicellulose. So hemicellulose is the one we spoke about earlier. It's composed of xylose, galactose, mannose, etc. And xylose is the most common found within the hemicellulose. So we used that there. Again, same route, the protection, selective deprotection, and installation of the activation group. So there have been no reports of the xylose or the cellobiose models in the literature at all. So this is all completely novel stuff. Very good in terms of water solubility in all of them. So discuss the right hand side here first of all. So these are the models that we produced using the xylose So we used the guaiacol, cedar-vanillin, isoeugenol, then the different esters, and again the beta-5 linkage here. So that was very good, getting that 71% yield, where otherwise it was getting sort of 19% yield. So very good, made that in a preparative scale. This is currently ongoing work in terms of the photocatalysis, as mentioned earlier on. So yeah, that's very interesting stuff there in terms of the products being received so far with the photocatalysis. If we look at the left-hand side now of this slide, we wanted to try and produce a sort of artificial section of biomass. So we took this glucose trichloroacetamidate, tetraacetate, and we tried to link it through the C5 xylose using the same conditions, the boron trichloride ethyl etherate, to produce this here, sort of artificial kind of cellulose, hemicellulose lignin kind of motif. I thought that would be quite nice. However, what we found was that whenever you try to do this reaction, the three products that were isolated were the glucose tetraacetate, so you're producing the free hydroxyl here, you're producing xylose, and you're producing guaiacol. So you're getting the liberation of the three species here. So you're seeing removal of the guaiacol, removal of the trichloroacetamidate unit, and you're getting them three products. So that didn't go ahead. That, again, that's under future work. So we're still trying to focus on getting that there made, because that would be a nice kind of motif of artificial biomass. And one other reaction that we just sort of done as a kind of Friday afternoon experiment was to see if we could link perform a double addition onto this sort of biphenyl species here with these two free hydroxyls. Now we knew that it was going to be complicated because of the difference in isomers here. So we obviously got the double wavy bond here is going to imagine, as you can think, it'll give you a headache in terms of the NMR. And the NMR was quite indecipherable, but we found that by mass spectrometry, we did produce this here molecule. So again, along with this artificial biomass kind of motif here, this is ongoing work to see if we can kind of produce more of these here and build up more and more representative model compounds for the catalytic systems to be tested with. So to conclude, we've produced more accurately represented biomass models. So the biomass models of this kind have not been produced before in the literature. These are being investigated now with titanium dioxide photocatalysis in a totally aqueous system, something again which hasn't been done. The only other model compounds that have been used before in terms of cellulose and semicellulose are glucose and xylose and stuff like that there. So to actually conjugate them to a lignin model compound is quite unique and quite good stuff. Sort of future work again, or more future work, is to extend the carbohydrate chains, sort of cellotriose, cellotetrose, and sort of build more lignin model complexity to build more advanced structures like that there. Some of the references. And then just like to say thank you to everyone for listening. Thank you to the EPSRC for the funding, and thank you to the University of Limerick for this opportunity. Thanks.
That's excellent. Thank you very much. Really nice talk. We have time for a couple of questions. There's a few coming in now. So what type of titanium dioxide are you using for catalysis?
P25, Degussa P25.
Okay, excellent. One question I have. So there's quite a lot of organic solvents been used to get to the biomass phase, okay? Are the green credentials of the approach somewhat compromised by the use of
yes,
especially if you're producing at scale?
Yeah, I mean, in short, yes. But we thought that if the ends justifies the means, kind of, we're getting more of an insight into these catalytic systems that, you know, although terrible using dichloromethane on a large scale, it would be theoretically worth it.
Okay. Okay, no, that's a perfect answer. If there's no more answers, I think we've actually just one more question. How do you analyze for projects, especially if you especially if you have several different molecules?
So we use HPLC refractive index, HPLC UV, we use NMR, and we also use LCMS for the elucidation of products and separation. So we use the RI HPLC for the sugar component, and then the UV for the lignin component, and then the LCMS for whenever we get the good separation of the compounds, and then final elucidation.
Okay, thank you, Christopher. Okay, so that brings this first of the afternoon sessions to a close. I will just thank all our speakers once again. The quality of the talks has actually been excellent. I've been really, really impressed. Our next session is on nanochemistry, and that will be chaired by Dr. Teresa Curtin. So thank you very much to everyone that contributed today.
Okay, welcome everybody. I know we're maybe 2 minutes early, so I will, maybe what I'll do is I'll just introduce the speakers maybe, and then by the time that's done, it'll be 3 o'clock. So sorry, my name is Teresa Curtin and I'm from the University of Limerick. We have 3 speakers this afternoon. So we have Sean Hennessy from NUIG. We have Gavin Irvine from Queen's University Belfast, and then our third speaker is Madhuri Dandamuji from Waterford Institute of Technology. I want to welcome everybody here. We're in for a very interesting 60 minutes or so. So what I might do now, because we're almost on time, I see we've got 50 seconds left, so I'll call on Sean, maybe our first speaker, to start sharing his screen. So what we'll do is we have 20 minutes each. So Sean, I'll give you a quick maybe shout at around 1 minute to go, but I'm sure you'll be within the 15 minutes. And then if there are any questions, just what you can do is just write them into the chat function. And I'll call them out then at the end of the presentation. So we'll have time, I guess, for 2 or 3 questions at the end. Okay, so I think we're at 3 o'clock now on the dot. So Sean, I'll pass the floor over to you.
Yes, can you hear me okay?
Yes.
Yeah, perfect. So thanks for the introduction. My name is Sean Hennessy. I'm a final year PhD student under the supervision of Dr. Pau Faras in NUI Galway. And today I'm going to talk about one of my projects, which is a prototype pyrene ruthenium molecular complex for the creation of innovative photoactive materials. So just to give a bit of outline about what I'll be talking about today. So I'm just give a brief background into light harvesting systems and the photoactive materials that we're interested in. The molecular systems that we've made in this project, the synthesis of them, and the basic photophysics of them. And then the key part of the work is the creation of a new ruthenium pyrene covalent framework system, its characterization and its tunability, and then we look to the future outlook of the applications of these materials. So just to talk about the background of light harvesting systems. So these systems, like light harvesting devices such as titanium oxide surfaces, have been used in oxidation processes and reduction reactions in many modern research. So they involve the oxidation of substrates and the reduction of substrates using natural light. And obviously these systems have good advantages, they being very green processes. They use renewable feedstock in the form of solar energy. They reduce waste, so they don't use organic solvents. We can use benign solvents such as water. And we can use tunable systems. So by attaching different catalysts to the devices, we can change the catalytic potential, the light harvesting potential, etc., to improve the catalysis of the system. Now, in terms of disadvantages, many of these devices have limited visible light harvesting. They also have rapid charge recombination, decreasing the catalytic output, and they also have low stability and longevity. So they tend to break down over time. They also might not be very good in thermal conditions, and they might not be very good over a long period of time in terms of its catalytic performance. So what we're looking into doing is producing new materials that improve on these disadvantages. And what we're looking at is the creation of framework materials. So here I've just shown publications in the last 20 or 30 years on light harvesting frameworks and photoactive frameworks. And as you can see, in the last 10, 15 years or so, they've increased rapidly in attention. However, we're still only looking at 50, 60 publications a year, which means they're a relatively underexplored area. So these materials can take 3 fairly common forms, and they tend to be metal organic frameworks and covalent organic frameworks. And they involve like I say, 3 different forms. One of them involves using photoactive linkers, so linking organic substrates that can link between metal sensors that are photoactive, so light harvesting. Alternatively, you can have photoactive metal clusters, so metal ions such as titanium, silver, gold, which can act as photocatalysts inside the framework. And finally, you can use encapsulation methods by forming a benign system using non-photoactive linkers and metal ions, and encapsulating a photocatalyst or a nanoparticle into the system, which is photoactive. However, what we're looking into doing is combining these two systems. So combining the advantages of metal organic frameworks, that is to say, the open metal site, and the advantage of covalent frameworks, that is to say, the structural stability, into these new materials or metal covalent organic frameworks. So by using a metal complex as the linker between covalently linked units. So to do this, we've looked into using a pyrene moiety as the linking covalent unit. And the reason for that in terms of photoactive materials is that pyrene is highly fluorescent, it's highly chemically and thermally stable, and it's relatively easily functionalized at the positions I've shown here. And then as for our metal complex that we're using to link these devices, we are looking into using metal diterpyridine complexes. They are linear in the form of the 4 substitution on the central terpyridine of linked to the metal. They're also photoactive, more so depending on the metal that you use in the center. They're highly chemically and thermally stable, much like the pyrene, and they have the catalytic center in the central metal. So in this work, we looked into creating a simple molecular system using a ruthenium terpyridine. We looked at ruthenium because ruthenium polypyridyl complexes are known to be very good photoactive materials, and linked that to a pyrene moiety to see if we have improved light harvesting. We then looked into creating a photoactive prototype complex, having the central pyrene substituted with 4 ruthenium complexes, and from there we looked into creating the ruthenium pyrene covalent framework. Now, to link these two together, we looked into functionalizing the terpyridine with an aldehyde group and the pyrene with an amine group, and to form an imine or a shift base type bond between the ruthenium and the pyrene. So we just had an hour of organics, so I won't go into too much detail here, but we started with 2-acetylpyridine and our acetyl functionalized aldehyde. In one step, we can form the terpyridine with the benzyl functionalized at the 4 position. We complex that with the ruthenium into one step, and we can hydrolyze the acetal to the aldehyde or the dialdehyde in a 3rd step. And in terms of the amine functionalization of the pyrene, we can do that in just one step, Suzuki coupling. So in terms of the simple molecular system, we looked into just having the monosubstituted pyrene and the monosubstituted aldehyde on the ruthenium, and coupling it just with a solo imine bond. And as you can see here in the UV vis, the pyrene has the very distinct band at 350, which isn't present in our free ruthenium, shown in red. And then when we couple the 2 systems together, we see that the MLCT, which is the ruthenium to terpyridine band,